simplify each of the following. So, if you have the square root of something squared, they are what we call inverse operations of each other. Square roots and squares cancel. This does not need an absolute value because the inside x is to the power of 1. A power to a power says you multiply. So x to the 1/2 times 2 becomes x. A cube root and a cube are inverses, so we get x. One-third to the power of 3, you multiply and get x. So we can then say that if the power outside matches the power on the radical, then it is equal to the inside. If the power outside matches the power of the radical, it is equal to the inside. We can also say a power to a power that our inverses multiplicatively are equal to the inside. That also allows us to make the connection that if it is to the nth root, that is equal to 1 over x. So the cube root and x to the 1/3, the square root x to the 1/2, the nth root x to the 1 over n are all equivalent statements. So the nth root is equal to x to the 1 over n. And what we're going to do today is talk about what we call rational exponents. The word rational in math means that you can write it as a quotient. If you think about the word quotient, it means division. So we are going to talk about exponents involving division. Don't seem so thrilled. There we go. There's my excitement. Yes. All right, rational exponents. Our goal today is to simplify and write radicals as rationals and vice versa. A rational and radical exponent summary. For any real number b and any positive integer n, we can say that a to the n, or rather I guess b, is really b, is equal to the nth root of b. As long as b is not a 0. You cannot take 0 to a rational power. We can, however, take the square root of 0, or the cube root of 0. It will always be 0. Anything to the power of 0 is always so start off easy. Take the variable, raise to a power, and rewrite it as a radical. So again, radicals look like square roots. A to the 1/5 would be the 5th root of A. It was talking about being positive or negative. If the outside number here is even, so if you have x to the 1/6 or the 6th root of x, then this automatically implies that x is greater than or equal to 0, because we know that the domain of anything to an even power has to be positive. The a's domain is all reals, because you can take the 5th root of positives or negatives. What happens if that exponent doesn't have a power of 1? So think back to your rule for a power to a power. A power to a power says we multiply. So this is the same as saying d to the 7th to the 1/4. So you could have the power of 7 inside, 1/4 outside. That's also the same as saying d to the 1/4 inside raised to the 7th outside. Powers to powers are multiplied. But we want to get this in radical form. So because the 1/4 is representative of the radical, so a radical has a power of 1 in its numerator, this is going to be a 4th root. And we can write the 4th root one of two ways. We can write it where the 7 is inside, or the 4th root where the inside is the variable only, the power is outside. All 4 of those things I wrote are what we call equivalent statements. They all mean the exact same thing. Multiple ways of representing one thing. So number 4, the goal is to write it as a radical. The denominator is the nth part of the root. The numerator is the power that stays to the variable. So you could write x squared to the cube root, which is probably the most common, but you could also write the cube root of x all squared. But 90% of the time, if you're going to see it out in your book or in math problems, it's going to look like that. We can do the converse of that concept then. So we can now take something that is written as a radical and write it as an exponent. So if it's the 4th root of z, that is the same as z to the 1/4. The 8th root of c is the same as c to the 1/8. Same thing. Rewrite it in exponential form. Outside power is the denominator. Inside power is the numerator of the fraction. But then if you go back to the beginning of chapter 7, we talked about the fact that you cannot have a negative exponent. So you would need to rewrite this as 1 over c to the 5/3. In number 4, you get x to the 4/6. What's cool about that is you can actually reduce your fraction and get the 2/3 and see the relationship between a 6 and a cube and how they would be related. Just like we can simplify radicals, we can simplify radicals and rationals in the same way. So if you have 81 to the negative 1/4, we know that a negative drops down to the denominator. So that's really like 1 over 81 to the 1/4, which is also equivalent to the 4th root of 81, which means I need to find a number that multiplies 4 times to get 81. So I need a number that if you multiply together 4 times, you get 81. So 2 times 2 times 2 times 2, 16. 3 times 3, 9 times 3 is 27, times 3 is 81. So the 4th root of 81 is equivalent to 1/3. So if you are asked to evaluate, you are simplifying. 2/16 to the 2/3. So what happens is everybody falls into the pattern of, okay, that's the cube root of 216 squared. But remember I said there are times it is helpful to not put the square inside and to put the square outside. So in this case, the cube root of 216 then squared is more logical, because the cube root of 216 is 6. So now if I don't have a calculator, I know the cube root of 216 is 6. 6 squared, I can do in my head, and I get 36. That's why there are also times where it is easier to simplify your fractions. So something was like 2 to the 4/6, it would be easier to make it 2/3 because it would reduce better. Okay, the 8th root of 256, all cubed. I would not anticipate we know it, but the 8th root of 256. 2 cubed is 8. So most of what we've done so far should make sense. It's pretty logical. It's really not anything new except for the notation. You've been simplifying radicals. You've been simplifying powers to powers. Now we're just sort of mixing or meshing them together. So go back to 7-1 and say, okay, what is the rule? Actually, I need 6-1. What is the rule if you have the same bottom and you have multiplication? So x squared times x cubed becomes x to the 5th. Because the rule is that a variable times a variable, you add your exponents, not multiply. You multiply when it's a power to a power. So a to the 2 sevenths times a to the 4 sevenths is equal to a to the 2 sevenths plus 4 sevenths. Or a to the 6 sevenths. I don't know why I use the same variables. But that is b to the negative 5 6. So again, no negative exponents. You must simplify, drop it to your denominator. And then if it doesn't specify, you can leave it in exponential or radical. Either one is fine. So if the directions don't specify, it is a choice. If it were a multiple choice test, usually the multiple choice matches the original. So 1/4 plus 9/4 becomes 10/4. And again, if you can reduce, you want to reduce your fractions. So 10 and 4, both divide by 2 to give you 5 halves. Rewrite our negative as a positive. The last part is just putting it all together with numbers instead of straight variables. So we have the 4th root of 27 over the square root of 3. So this is where if it doesn't match, we usually cannot simplify. So yesterday, if there was a 4th root and a square root, the rule was that they were not like terms. Well, we're rewriting these as rational exponents allows us to create like terms. So this is 27 to the 1/4. Three to the 1/2. We know that we cannot have a radical in our denominator, so we can rationalize. So that's one way we could start this problem by saying, okay, we're going to multiply by the same square root. Now we'll get rid of the radical in my denominator. The reason I changed them to fractions is because we can make fractions add together. Also, what do you know about the number 27? 27 is 3 times 3 times 3. So the rule is you can't take or add two things together unless they have the same base. So this is really like 3 cubed to the 1/4 times 3 to the 1/2. A power to a power gets multiplied. now the bottom numbers match. They're both 3s, so we can add the fractions. So 3/4, 1/2 is the same as 2/4. So I get 3. 3 plus 2 is 5. So the 5/4 over 3. In the back of your book, more than likely they're going to treat this one like 4/4, so it's like a 1. So they're going to say you have 3 on top, 3 on bottom, 5/4 minus 4/4 is 1/4. Because if the top and bottom are the same, you can subtract. Again, that's one way to do the problem. Somebody may have thought differently, and that's fine. That's what makes sometimes these problems a little unique. We have the cube root of 64z to the 6th. So again, you can think of this as 64z to the 6th to the 1/3. And if you go back, 64 is 4 times 4 times 4. Cube root of 64 is 4. A power to a power gets multiplied. And we get z squared. And then the very last one, complex conjugate. We can't have a square root in our denominator, so we multiply by its conjugate. So the bottom, we already know 3x to the 1/2 times 3x to the 1/2 is 9x. A half plus a half is a whole. The middle terms are going to cancel because they're difference of squares, complex conjugates. 2 times -2 is -4. And then you have to FOIL your top. So first, outer, inner, last. Combine like terms. You're done. Your homework and your notes are very, very similar in the order they go. So each example will match kind of the set of problems. Again, I anticipate the most difficult will be like the last 4. Other than that, just can you apply the rule of nth root to a power?